Okay, so let's start off with our discussion of General Chemistry 1 with Chapter 1, which deals with some topics that you should have met before in your high school or introductory chemistry experience. So we'll be talking about matter and measurement in this chapter. So before we get started, we need to get into some key terms. Firstly, we'll define what chemistry is. Chemistry is, of course, the study of matter and the changes that it undergoes. And as far as the term matter is concerned, matter is basically anything that has mass and occupies space. So matter is basically the stuff, the material that things are made of. Some other key terms you should have met before, as I said before in your high school or introductory chemistry experience. Atoms, these are the smallest distinctive units in a sample of matter. And then we have molecules, which are basically collections of atoms to form a unit, which is held together by covalent bonds. So a simple example of a molecule will be water, because each water molecule consists of 2 hydrogen atoms and 1 oxygen atom. Another example, excuse me, is that of oxygen gas, because it turns out that oxygen exists in nature as a diatomic gas, which means basically that each molecule exists where you have 2 atoms making up that molecule, as you can see in this diagram right here. Okay, some other key terms. Whenever we talk about the composition of a substance, what we're talking about is the atomic makeup of the substance and the relative amounts of each element present in that substance. So going back to the water example, you'll see that, as I said before, water consists of 2 atoms of hydrogen and 1 atom of oxygen per molecule. If you break up water into its constituent element, then what you'll find is that 11.2% of the water by mass will be hydrogen, and the rest, which is 88.8%, will be oxygen. All right. Now you might be wondering, why is it that hydrogen has such a small percentage, even though the number of oxygen atoms is twice that of the number of hydrogen atoms is twice that of oxygen? And that's because the simple answer is that hydrogen is lighter or less heavier than the oxygen atom. So therefore, the 1 oxygen atom actually has a greater mass than the 2 hydrogen atoms collectively. We're going to talk more about composition later on, because later on, you're going to see that you can use composition data to determine the actual makeup of a substance at the microscopic or molecular level. Okay, some other terms that you should have been exposed to. The term property. Whenever we use this term property, we're talking about those characteristics that you can use to identify a particular substance. And these properties can be put into one of 2 categories. You have physical properties, which, as stated here, are properties that are displayed by a sample of matter without the substance undergoing any change while you're observing that property. So some examples are shown here. Physical properties include things like mass, color, volume, temperature, density, melting points, etc. And then we have chemical properties, which are properties that, when observed, involves that substance undergoing a chemical change or a change in composition. And some examples of these would be flammability, toxicity, reactivity, acidity, and there are others as well we can talk about. These are all examples of chemical properties. So if we look at this picture here, we have copper metal here in a dish, and also in the same dish, occupying the other half of that dish, would be ethanol. Now, the observation, as far as copper is concerned, that it is reddish brown in color and an opaque solid, that is basically a statement of some physical properties of copper, because we can make these observations without copper undergoing any reactions whatsoever. On the other hand, when it comes to the ethanol here, as you can see, it is basically being burnt, right? So basically a chemical reaction is taking place where ethanol is being converted to other substances, mainly carbon dioxide and water. So therefore, the fact that ethanol is flammable is a statement of the particular chemical property exhibited by ethanol. Okay, so that's as far as physical and chemical properties are concerned. And then related topics or related terms, physical change and a chemical change. Let's deal with the physical change first. A physical change is one where a change is occurring, but there's no change in the composition of the substance that is undergoing the change that you're observing. All right, so things like evaporation, things like melting, cutting a piece of wood, or dissolving sugar in water, these are all examples of physical changes, because what they all have in common is that even though there is a change that you can observe, there's no reaction taking place, there are no new products being formed, so therefore we consider these changes to be physical changes. On the other hand, chemical changes, otherwise known as a chemical reaction, involves a change where new substances are formed as a result of the changing composition of the substance. So some examples of chemical changes include the burning of gasoline, dissolving metal in acid, and the spoilage of food. So these are all examples of chemical changes. So this picture here shows you I think this is a stove, portable stove, where you have propane gas being the fuel source, and in order for it to be ignited, it has to be vaporized. So therefore, it is normally stored under pressure, but when it's released, it's converted from the gaseous state to the liquid state. So that conversion would be a physical change. But when it's exposed to a flame here, and therefore it produces light and heat energy, then basically a reaction will take place where the gas, which I think is propane in this case, will undergo what we call a combustion reaction to form carbon dioxide and water. We're going to talk about those reactions or reactions of that type, combustion reactions, later on in this course. I think we'll talk about it in chapter 3 or 4. Okay, let's talk about the classification of matter. Again, this is something you should have met before. So this flowchart shows you basically the different categories of matter. We're going to talk about them in more detail, but basically, as you can see here, all atoms and molecules come together to make up basically all matter, which can be divided into pure substances and mixtures. As far as pure substances are concerned, that can be further subdivided into elements and compounds, whereas mixtures can be subdivided into homogeneous and heterogeneous mixtures. So we're going to talk about these subcategories and categories in more detail in the following slides. So let's start off by talking about what we mean by a pure substance. A pure substance is basically matter which has a definite or fixed composition that does not vary from one sample to another, all right? And all substances are either elements or compounds. Now, when it comes to elements, elements are basically substances that cannot be broken down into simpler substances. And if you consult any periodic table, you'd notice that that contains a list of all the known elements, and these what these elements have in common, as I said before, is that you simply cannot break down these substances into anything simpler by chemical means, all right? As far as a compound is concerned, a compound is a chemical combination of two or more substances. And as a result, the relative amounts of the different elements present in a compound is fixed, right, in terms of their proportions. So for example, the water example we saw earlier, there's a 2-to-1 ratio between the hydrogen atoms and the oxygen atoms present in a molecule of water, and that translates into fixed proportions by mass. As we said before, the percentage of oxygen is 88.8% in any sample of water, and the rest would be due to the hydrogen. Some other examples of compounds are shown here. You have carbon dioxide, you have sodium chloride, and you have sugar, and that's what they all have in common. If you break down these compounds into their constituent elements, what you will find is that in each case, the percentage of the different elements present in the compound will be fixed. Okay, so let's move on now to a discussion of mixture. Now, one big difference between a mixture and a compound is that, unlike a compound, the composition of a mixture is not fixed, all right? But let me just say first what a mixture is. A mixture is basically a physical combination of two or more substances, right? And as a result, in a mixture, what you'll find is that each substance will retain their properties. So for example, if you add, let's say, sugar to water, the sugar dissolves in the water and you end up with what we call a sugar solution. The sugar that is present in the water will still retain its properties, and the water, of course, will still retain its properties. And that's basically what a mixture is. And there are two types of mixtures. You have what are known as homogeneous mixtures, where in that particular mixture, the composition of that mixture would be the same right throughout the mixture, all right? And some examples of homogeneous mixtures are shown here. Soda pop, which is basically, for the most part, carbon dioxide dissolved in water, which may also include some flavorings and so on for taste. So that's an example of a homogeneous mixture. Salt added to water to form a solution. 14 karat gold, and many plastics are homogeneous mixtures, all right? Now, the thing about 14 karat gold is that I don't think they are pure substances in the sense that it's only the element gold present. It might be mixed with other things, but the point here is that that mixture is homogeneous as well. Now, when it comes to heterogeneous mixtures, the big difference is when you compare heterogeneous mixtures to homogeneous mixtures is that you don't have a uniform distribution of the two components or the different components that is present in that mixture. All right, so one simple example of a homogeneous, or I should say a heterogeneous mixture, which is not listed here, would be oil and water. If you add cooking oil to water, you're going to end up with two layers, right? You're going to end up with oil at the top and water below. And of course, you'll observe a boundary of separation between the two components, right? So that's an example of a heterogeneous mixture because it's not uniform. The top part contains the oil and the bottom part contains the water. And you see some other examples of heterogeneous mixtures listed here: adhesive tape, CD, a pen, battery, and so on and so forth. Okay, so most stuff that exists in nature exists as mixtures, either homogeneous or heterogeneous mixtures. There are very few instances in nature where you might be able to identify a substance as a pure substance in nature. Okay, we're going to stop here, and then the next video will be dealing with the scientific method. Okay, so until next time.